Now, before we start with the meat of this episode, which is the testing of the Spacer custom chip-in system, I need to issue a correction and a couple of clarifications about things I said in previous episodes. Particularly, I believe it was in episode 8 that we discussed this bodge here to the prototype video board. And there I said that by using this little charging resistor to charge this capacitor here hanging from pin 1 of Skunk, which is the global clear for the flip-flops in Skunk, we can sort of keep Skunk in a reset mode until this capacitor charged, and keep all the flip-flops in a reset state until this charging finished and the power rail was stable, and that's why it helped with the stability of the chip. And I even remarked to you back in that episode that it was strange I couldn't find this feature in the datasheet. Now, the reason I couldn't find this feature in the datasheet is that this feature doesn't exist at all. This bodge here was helping a lot in the reliability and stability of the video circuit, but for a completely different reason than what I told you. I was interpreting this global clear here, I was tempted to interpret it as a regular reset pin that you have in a microprocessor, but it doesn't work that way at all. It works in a completely different way. The reason this resistor and this charging capacitor here were helping is that they were, in one way or another, having an electrical influence in the power rail. They were delaying, I believe, the start of this chip here, which is the buffer. This is the buffer through which the clock signal passes before it goes to Skunk. So I think this buffer here was having a delayed start because of the electrical influence in the power rail of this charging capacitor here. That's what I think right now. But even if that's not the reason, whatever the reason is, it's associated with the effect of this charging capacitor here, charging slowly through a 10k ohm resistor. It had an electrical effect on the power rail, and that's what was happening, helping the stability of the system. This pin here is not a reset pin, it's a global clear. Now, I have to explain to you both these things. What is the difference between a reset and a global clear, and why I think that delaying the start of this buffer here was having the desired effect. So let's get to it one by one. First thing to notice is that an actual reset pin works like this. It's usually active low, so when the level is low, nothing happens in the chip. Nothing happens in the chip. It's held in a reset state, irrespective of any edge, rising edge or falling edge. If the signal is low, the chip is held in a reset state. And only after the signal goes high, in other words, the reset is no longer active, then stuff happens in the chip. Now, the global clear of the CPLD devices does not work like this at all. It works like this. It only triggers a reset on the rising edge of the global clear signal. So even if you hold the signal low during power on, which is what I was doing with that capacitor and that resistor, stuff will still happen because there is no rising edge. It's not a reset pin. It's a global clear pin, meaning that only when there is a rising edge in the signal, then the flip-flops are set to 0. And if you keep the signal high after that, stuff will still happen. And if it goes low after that, stuff will still happen. The falling edge will have no effect either. So you see, it's a completely different functionality. You have to have a rising edge for a moment for the flip-flops to clear. Holding the signal down has no actual effect. Now, here's what I think the effect was that charging capacitor was actually having. It was having an electrical influence in the power rail that delayed the startup of the buffer chip through which the clock signal passes before it gets to Skunk. And if that chip starts late, then Skunk gets the clock late. It will get the clock only after it has completely powered on. Now, why is that relevant? Well, if you go to the application notes of a microchip, we've reviewed this before, but let's look at this again. There are several requirements for the power-up of the CPLD to complete correctly. And one of them is right here. All input and feedback setup times must be met before driving the clock pin high. Before driving the clock pin high. And by delaying the moment when the buffer powered on, I think that charging capacitor was making sure that skunk would only get the clock pin driven high after all input and feedback setup times were met. So it was serendipitous. It was just a good coincidence that by doing what I thought was driving a reset pin low, that it actually helped a lot, but not at all for the reason I thought. And if you look at the next condition here, condition 3, the clock must remain stable during device power up. So you see, it's very useful to delay the moment when the clock actually comes into the CPLD, when it comes into skunk, by keeping the buffer through which the clock signal must pass powered down until after the CPLD is fully powered up. And that's the modification I actually did to get the final version of the video circuitry, including the final board of the video circuitry. So here's the updated schematics where we can see the main changes. I'll guide you through it. One of the changes I did is can be seen here. So this is, well, it should now be skunk. It's no longer skank. So this is a skunk. I added an extra pin called buffer enable. And in the hardware description, I basically make this pin high. I just set it to 1. Always, but of course it will only be set to 1 once skunk has fully powered on. So this pin will actually only go high when skunk is ready, fully powered on. And I want to use this value here to enable the buffer, the 74244, because the clock signal comes in here. That's where is it? Oh, here. The pixel clock goes through the buffer, out the other side, and now it's the buffered pixel clock, and it's this BP clock that goes into skunk over here. BP clock goes in here. So what we want to do is to delay this signal until skunk is fully powered on, which will be signaled by this BE pin here going high. So we want BE to control the output enable pins of the 74244, because for as long as the output is disabled, the pixel clock will not pass through and therefore will not get to skunk. Now there are 2 output enable pins. These are this pin here, the second output enable, and the first output enable. So it's pins 1 and 19. Now we could think, well, let's just put BE wire there, but that wouldn't work because those pins are active low. While this pin here, if we say, okay, let's drive this pin low, then it will be low before skunk powers up. The only way to make sure that the value here will correspond to skunk being fully powered up is if we make it high, if we drive it high. So we need an inverter. We need to invert this signal and only then connect it to the output enables of the 74244 or the buffer. So we'd use a 74 logic chip full of inverters, but that would be a total overkill. We only need one inversion. So we build a little inverter ourselves, and that's what you see here. We just use a general purpose NPN resistor, the 547B, which is very common in Europe. In the US, you have other equivalents that are very common. And we hang the BE signal, which is this here, coming out of skunk, we hang it to the base of this transistor. Now, if you want to see how it works, imagine that there are no resistors here. Pretend there are no resistors. Then this little transistor is just a switch. If there is current flowing from the base to the emitter, then the switch is closed, and this point will be identical to this point. Collector and emitter will be the same, will have the same potential. Now, when there is no current flowing from the base to the emitter, then the transistor will be open, and this will be separate points. The potentials will be different. Now, of course, if we add no resistors, the moment we drive PE high, you would have a short circuit here because collector and emitter would have the same potential, but there is VCC hanging from the collector and ground hanging from the emitter, so you just short VCC to ground. So to avoid that, we need to put a current limiting resistor here. I chose a 10k ohm resistor, and we also don't want, this would solve the short circuit because when the transistor is closed, you have a 10k ohm resistor between the potential for VCC here and the potential for ground here. This point would become ground once the switch closes. This ground here would go straight to that point, but you would have a resistor limiting the current. You wouldn't have a short circuit, but you would still have current flowing from base to emitter, and that may be still too large a current to be driven by this little pin here from the CPLD. And since the whole thing is about potentials, I will limit this current here with another current limiting resistor of 10k ohm. And this is now an inverter. Whenever BE is low, this point here will be high. And whenever you drive BE high, this point here will be low because this switch will be closed and this point here will be ground. And that's the point where we take the output enable for the buffer. So the buffer will only be enabled after skunk is fully powered on. And this helped a lot. This made the second and final interaction of the prototype board of the video circuit 100% reliable. I did a few other things. I added another decoupling capacitor. I added some pull-up resistors to the JTAG programming ports just to prevent the chips going to a JTAG test state because of some fluctuations. So but that's not really required. I did it just because, well, I'm paying for another interaction of the board as well. I might just as well do everything that I can think of to make it stable. It's easier to explain now that if we look at the design of the board itself. This capacitor here, it's an extra decoupling capacitor I added close to the two memories, and the reason is this is a 100 microfarad capacitor. It's the largest in the system. The other one is there right at the input, and that's very far away from these two memories, far away from these sides of Skunk and Kavia. So I added one more there, and these are the little pull-up resistors connected to some key signals of the JTAG programming port. This one is another one, and these two are also pull-up resistors for the JTAG port, just to prevent it from suddenly going into a test state. It wouldn't do that, but just to make sure that it really won't do that, these were added. And this is our inverter transistor. So the BE signal comes from this pin in Skunk, goes through this current limiting resistor of 10k ohm into the base of that transistor. The emitter is connected straight to ground. You don't see it here because I'm using the hidden ground plane in the middle layers. And this is the collector, and it's connected to VCC via this pull-up resistor or current limiting resistor as well, R5, just as you saw. And this makes sure that this chip, which is the buffer, only is enabled after Skunk is fully powered on. Now this board here now, it's completely stable. This is the final design. The only thing I regret is that I'm still using the old name for Skunk. I'm still using Skank, but I'm not going to change it. Or maybe I will, maybe before I put it on GitHub, because this is just the silkscreen layer, so there is no problem in changing this without issuing the files. It will certainly work. It's just a silkscreen. I will update this in the silkscreen. Maybe I'll do it right now. I'll do it right now. Skunk. Save. Come on, save. Yeah, it's saving. So it is done. So this is what will eventually go on GitHub. I just need to document it before I do that. Oh, there is one other thing I did. I now am using a linear regulator instead of a switch mode regulator that I was using before. But the pinout here is such that you can use either. You can either put an inefficient linear regulator here, a 7805, classical in retro computing. You can either use that. It's very cheap. It makes sure that the VCC rail has a monotonic increase when you power it on. It adds no jitter, it adds no oscillation, but it gets very hot, so you need to use a heatsink here, a heat dissipator, and it's not very efficient. You can use that if you want, or you can use the more expensive but a lot more power efficient switch mode regulator, which will fit on the same holes here, the same pinout. So the board is more flexible now. So here's the new board, updated, still pretty high quality like the previous one, quite happy with it. And I've just populated it, and that's what we get. So the main changes are I'm using now a linear regulator. I use some thermal compound to put a heat sink on it because this thing gets pretty hot. It's also slightly lifted from the board, and this is on purpose, so there is space for air circulation underneath, because these heat sinks, they work through convection. They heat the air here in between these fins, and the air goes, and then cooler air from underneath flows in and then goes up. The other main change is this transistor here, which together with this resistor and this resistor form the little inverter. And right now this is working like a charm. It's very stable, starts on properly every single time without fail. Now, one last thing before we get to testing Spacer. There is a bug in the couple compiler that I encountered. There is a quick and easy way to circumvent it, but you will see the hardware description and you will see things in there that you ask yourself, why is it doing this here? Well, it's to circumvent the bug. So I need to explain to you what is actually happening. Spacer has a 24-state shift register. So it will have 24 of these little things here, this circuitry. This is the actual hardware that's physically in the CPLD. There is a flip-flop there holding a state. I need 24 flip-flops for the shift register, so there will be 24 of this thing here, the flip-flop and all the auxiliary logic around it. Now, the couple language is such, let me clear this out, if you just want to refer to the output Q of the flip-flop, to that value, it's very easy. You just say, okay, alt var, the output variable associated with that flip-flop, and if this buffer here is enabled, then the same alt var will be here on the output in. So it's very simple. And if you want to use this alt var value for extra computations, then you just refer to it the same thing, alt var, and the compiler will just take the inverted output of the flip-flop, which feeds back into the fuse array, and from there it can be used in other equations. Now, in either case, you just say alt var. So to build the shift register array, I just refer to the respective names of the 24 variables, the 24 states at the output of their respective flip-flops, and I connect them one to the other via this feedback line here, which is alluded to simply by the name of the variable, output variable, or alt var. Now, what was actually happening when I did this is that the compiler was taking this value here after the buffer. And because I was enabling the buffer with the output enable signal only after the shift register was completely filled with data, only after that I was enabling this buffer, then the whole thing wouldn't work, because as I was trying to fill the shift register up by taking this value here after the buffer, it was taking nothing because the buffer was not enabled. So this feedback here would be 0. It would have no value because the buffer was not enabled. Now, this should only happen when you refer to altvar.io. This extension here, .io, refers to this point here after the buffer. If I don't add .io, if I just say altvar, then the compiler should be taking this value here, which will be fed back into the fuse array regardless of whether this buffer is enabled or disabled. But that's not what was happening. It was taking the .io value, and therefore by disabling the buffers nothing was working. So I had to circumvent that with some creative modifications to the code that I was advised to do from by Microchip themselves, by their support department, which has been very helpful, by the way. They replied very quickly and their workaround worked. So you will see that workaround in the hardware description. And one final update or correction from what I showed you in episode 9. In the previous episode, I had the character memory here at the top of the address space and the video memory here in the 2 kilobytes just below that. Now that works well for the Z80 because the reset vector of the Z80 where it starts is address 000 in the SRAM chip 1, which we can easily reserve for the reset vector of the Z80, but in the 6502 the reset vector is right here at the top of the address space, 3 or 4 bytes, 3 or 4 addresses just below the top, the FFFF. And if we had the character memory here, that address would be occupied. So that's the reason I swapped them. Now the video memory is on top and the character memory is just below, which is what I'm showing you now. What I'm showing you now is the final version. And this leaves the top of the address space here free. And the reason is that, so we can put here the reset vector of the 6502 to be somewhere here. And the reason this is free is that for the video DP RAM, although we are reserving 2 kilobytes in the address space for it, the screen is only 40 times 30 characters. That means the video memory actually occupies only 1200 bytes instead of 2048. So we have over 848 addresses here which are free, and we can use it for whatever purposes, like the reset vector of the 6502. That's the reason this change was made. And now just one very final change, an update. In the previous episode I was using here a non-maskable interrupt request. I have decided now that it's better business to use just a regular interrupt request, because then I have more flexibility. For instance, if a program is running and then it asks for the user for some keyboard input, I don't want to be forced to use a non-maskable interrupt for that, because the program may want to finish something before taking that input into account. And using an IRQ request, a regular interrupt request, I preserve the option to either mask it or not mask it. So I will use a IRQ instead of the NMI. Now, these are all the changes now. So here is the hardware description of Spacer, which, as you will hopefully see, is much easier to understand than the schematics that I've shown in the previous episode. These are just property declarations for the hardware compiler. We don't need to get into these right now. I discussed some of them before. Then we have the declaration of all the pins of Spacer. Many of these you have seen in the previous episode being discussed. That's the reset pin. That is the shift clock that goes from the ATMEGA microcontroller to Spacer. These are outputs of the dual-ported memories. We have the video BZ, that's the BZ output of the dual-ported video memory, and this is the same for the character memory. We had a discussion about that in episode 8. How to use these BZ signals to make sure that we write correctly to the dual-ported memory, even when the other side of the memory is being read from the exact same address. So when this BZ signal is active, and it's active low, we have to wait a little bit, because if we proceed normally, the value we are trying to write will not be written. This is the read-write signal. That's the CPU clock that comes, I'm sorry, this is the CPU clock that goes to the CPUs, and it's generated based on the oscillator. This is the serial output of the ATMEGA, which is an input for Spacer. This is the left-right flag for the shift register that we've also discussed in the previous episode. And this is the buffer enable signal, just like I'm using now in Skunk, in the video part. I'm using that same technique here in Spacer to make sure that Spacer does not get any clock before it's fully powered up. Now this is the CPU choice that we've discussed in episode 9 as well, the clock speed selection. These are two inputs of Spacer, and they come from the ATMEGA microcontroller. And these are the 4 chip enables that Spacer generates to enable the right memory depending on the address that it finds on the address bus of the system. So this is a chip enable of the character memory, the chip enable of the video memory. This is the chip enable of the high RAM, that's the high memory, one of the 2 SRAM chips. And this is for the other chip, the low memory. And then we have the shift register latch that we've also discussed in the previous episode. These are all the 24 states of that shift register we've discussed before as well, which has 16 bits for address and 8 bits for data. Then we have some field declarations, which are just a neat way to refer to all 24 states with one statement, instead of having to make the same statement 24 times, one for each of the flip-flops. If we declare a field, whatever we state about the field, we are stating for all 24 states, all 24 flip-flops. Now, so this is a state that corresponds to these signals in here, the shift register outputs, and then there are some internal states declared as a pin node, and that's just shift register 0 to 23 instead of shift register output 0 to 23. And this is just a way to circumvent a bug in the couple compiler. There is no need for this declaration of a pin node. Officially, this should be enough. But I'll tell you later what the bug is. Right now we don't need to worry much about that. That's a declaration for the internal states of the shift register. And then there are some handy declarations here of what a shift left and a shift right means. So this is a shift right, and you see that we just shift the states to the right, ending at 22. State 23 then falls off and is lost, and then we append a 0 to the left. And the same thing for shifting left. State SR0 falls off from the left, then we get SR1 to 23, and then on the extreme right we append the state as well, but instead of 0, that will be the serial output of the ATMEGA, which is a serial input for Spacer, and this is where that input is used. And then we have the clock, which basically comes from the oscillator, and the shift register output enable, which comes from the ATMEGA microcontroller, as we've also discussed in the previous episode. There are 4 states which are internal, that's why they have a pin node instead of a pin declaration, and these are states of a clock divider, a little counter that will be used as a clock divider to generate the CPU clocks. Now the buffer enable is just assigned a high value, a 1, and it will be 1 only after Spacer is fully powered up, and that's what will enable the 74HC244 buffer to generate the clock. In other words, Spacer will only get the clock after it has fully powered up and it has been able to put this BE signal high on its output pin. Now that's the memory logic. We've discussed this at length in episode 9. We have all the 4 chip enables here, 1 for each of the 4 memory chips used in the system. The logic is exactly what you saw in episode 9, except that it's now inverted because the chip enable is active low. So whatever activates the chip should be inverted here. And this one in the original was inverted. If I invert it again, then I just get the shift register state 15, because that's what corresponds to the address line 15. Now I'm using this extension .io here because that corresponds to the pin value, not to the output of the shift register. And the reason is here we are reading what is on the bus, not the address that is being produced by the shift register. Because even if another system component puts an address on the bus, say a CPU puts an address on the bus, we want to be able to read that even though that address will not be an internal state of Spacer. That's what this extension .io means. Instead of taking the output of the flip-flop associated with shift register position 15, we take the pin value associated with that flip-flop instead. So this will get the values of the bits of the address present on the address bus, even if that address is being put on the address bus by another system component, one of the CPUs and not Spacer. So this logic activates the correct memory based on the address that is on the address bus. And then here we have the clock management logic. In episode 8, we discussed that we needed to handle the busy signal. We cannot just assume that if we perform a write cycle to the dual-ported RAM, that write cycle will happen correctly if we ignore the busy signal, because sometimes there may be a concurrent read on the other side of the memory from the same address. And when that happens, the memory will issue a busy signal, which basically is a request for you to wait a little bit longer with the write cycle. So this is what this value, pause, does. It waits a little bit longer when the busy signal is active, and it's active low, that's why it's being inverted here. Now we need to do that once for each of the two dual-ported memories. So for the video memory, if this value is low, in other words, active, and if we are performing a write, when RW is 0, that means a write. And why do we need to choose that? Because when we are performing a read, there will be no problem anyway. The memory can serve two concurrent reads from the same address. The problem is when you're trying to write. So we will restrict the pause to when you're trying to write, and when you're trying to write from the corresponding memory. So in this case, if the chip enable of the video memory is active, and it's active low, and we are trying to write to the video memory, and the video memory reply by saying, I am busy right now, then we will pause and wait. Or, this is an or, the same thing, but for the character memory. So when the character memory issues an active busy, and we are trying to write to the character memory because this is the chip enable that is active at that moment, then we will pause. Now, then we have the clock divider. It's a 4-bit counter which uses toggle flip-flops. This is a very classic way of implementing a counter. If you want to see details, just type on Google binary counter with toggle flip-flops or T flip-flops, and you will find information about it. Now, it's clocked by the clock signal that comes into spacer, which happens to be the same clock signal that goes into the ATF MEGA microcontroller. The counter will be reset on the rising edge of the reset signal, and this is the CPU clock output. This is the clock that spacer will produce for the CPUs based on the input clock. Now, what's going on here? Now, the comments here may help. The 8 MHz CPU clock is the fast option for both the Z80 and the 6502. So we do not need to check which CPU choice we've made, because it's 8 MHz regardless of the CPU. All we need to check is the clock speed, and if the clock speed CLKS is high and C0, which is this state here of the counter, is active, and we are not trying to pause, then there will be a clock. And what will be the frequency of that clock? Well, if we take C0 instead of CLK, C0 will have half the frequency of CLK, because state C0 will toggle at every cycle, and that means that there will be a rising edge in C0 only every second cycle. So by taking C0 here, we ensure that the clock will be an 8 MHz clock, provided that we are not pausing, and if the clock speed choice is for a high clock. Now, when a clock speed choice is for a slow clock, in other words, when CLKS is 0, that's why we are inverting the signal, then the result will depend on whether we are choosing a Z80, which means that CPU choice will be 1, or a 6502, which means that CPU choice will be 0. That's why this inverter. And then we will take the state C2 of the counter, provided that we are not pausing. When we are pausing, the clock will just stop for the period during which we are pausing. But if we are not pausing, it will just be C2. And if you look at the frequency of the rising edge of state C2 in a toggle counter, you will see that it will have 1/8 of the original frequency, which is 16 MHz. Clock here is 16 MHz. So we will get 2 MHz if we tick the clock based on the rising edge of state C2. And then here the same thing, but for when we choose the 6502, and then we will pick state C3, and then there will be a division by 16 if we take this state here, and therefore the clock will be 1 megahertz. So depending on these two values here that come from the ATmega, the clock will be either, the CPU clock will be either 8, 2, or 1 megahertz. And that will also depend on the pause. When the pause is active, when we are pausing, we should see on the oscilloscope that the clock signal is withdrawn for a little while. It just stops ticking. And once the pause goes inactive again, then it starts ticking again exactly from where it stopped. Now, finally, we have the shift register logic in here, which is much easier to understand in a few lines of hardware description than it is on a schematics. So the shift register clock, that's the .ck here, will simply be the shift register clock, or the SC output from the ATmega microcontroller. So it's the ATmega that will clock the shift register in here, just as we discussed in the previous episode. Now I'm saying SRO instead of shift register, and actually there should be no difference. They are identical, as you see in this statement here. So you can read shift register .OE here, it's the same thing. So the output enable of the shift register will be the shift register output enable signal from the ATmega microcontroller. So the ATmega controls this as well. And then I'm equating the two, and you might think, well, wouldn't the compiler just optimize it away and make everything just one shift register? That's exactly what the compiler will do. So this is just a way to circumvent a bug in couple. It has no actual meaning. And the asynchronous reset will just be the reset signal. And now we have three conditions like we discussed in episode 9. If we are trying to do a shift register latch, in other words, if we want to acquire the values of the data bus which are connected to pins of spacer, if you want to acquire that value and parallel load that value into the shift register, then SRL, or shift register latch, that signal from the ATmega microcontroller, will be high, and therefore what we will do is wire the shift register.io. In other words, the pins of the shift register connected to the data bus, we will wire them to the .D, or the D input of the flip-flops. And then when the clock ticks, the output Q of all the flip-flops will just simply have the value that was on the bus at that moment. So this is just a parallel load of the shift register with the contents of the buses. Now, so this is not a shift, this is just a parallel load governed by the SRL signal that comes from the ATmega microcontroller. Now, we may want to shift as well. So when the SRL signal is low, as in these two lines here, we want to shift. But then are we going to shift to the right, as in this case, when LR is negative, also a signal coming from the microcontroller, or are we going to shift to the left, which is when LR is positive? If we are going to shift to the right, then we just take the contents of this field here, shift one right, and when we want to shift to the left, we take the contents of this field. And as we saw all the way up, the declarations of these two fields here, the shift right just appends 0 to the left and then shifts everybody one position to the right, and the shift left does the same thing to the left, except that we append the serial output value from the ATmega microcontroller on the rightmost position. And this is how we can shift things in and out of the shift register in order to write to the memories or read data from the memories. Now this is the little Arduino sketch we will be using to test Spacer. Again, I'm using an Arduino MEGA still, but that's just for testing purposes. At the end I will be using an ATmega 328P chip, not a whole Arduino board. This is just for test. So that's the sketch for the test. It's very similar to what we used in episode 8. In the main loop we just write X's. 61 is the code for an X. We just write X's throughout the screen, and then we clear the screen with that little routine you saw before for the clear, using the CERBERUS print function that we also discussed in episode 8. Now let's look at the differences. We are adding this shift register function to the sketch, and what it does is the following. The first thing it will do, because it's a set shift register, it will be writing things into the shift register. The first thing it will do is to set the output LR, left, right, high. In other words, we are going to shift things to the left, because to write something to the shift register, we shift to the left. To read the states of the shift register out, we shift to the right, because that's where the serial input of the ATmega microcontroller will be connected to. So the first thing we do is, okay, we set LR high, we are going to shift to the left, and then we use this handy function of the Arduino IDE, which we can also use when we use the ATmega alone. It's called shift out. Basically what you say is the pin, and this will be the serial output. Then you give the clock signal, which will be the shift clock, another pin. Then you tell whether you're going to shift the least significant bit first or the most significant bit. In this case, I'm shifting the least significant bit first. And then the address, which are the contents you want to shift. And those contents are just here, an input of the function. It's an unsigned integer, so 16 bits. That's the value you want to shift into the shift register, the 16 bits of address. The other parameter that you get when you call the function is data, because you want to shift in an address and a byte of data. So with the first call to shift out, we shift, this is shift out from the point of view of the ATmega, but it will be shifting things into the shift register of spacer. So we will shift into spacer the first byte of the address. That's the lowest, the least significant byte. This function here only works byte per byte. So we make a first call for the first byte of address, and then we call that same function again with the same pins, the serial out, with the shift register clock, least significant bit first, and then we do it for the second most significant byte of address. So we are doing the same thing twice, because the address is an unsigned int, so it's a whole 16 bits here. And then we will shift out from the point of view of the ATmega, or shifting into the shift register of spacer, the 1 byte of data. Although data is also an unsigned int, we know that the value here will be restricted to 1 byte, so we call the function only once, and it will shift out the full byte of data. This is how you set the shift register, by shifting things to the left in it, both an address value and a data value, which together will form 24 bits, and the shift register is 24 bits wide. Now, how do we use this function here, set shift register? We use it from the new version of CERBERUS print. It's very similar to what you saw before. We get the two coordinates, x and y, at which we want to print a token, or a character identified by a token number. This is the character ID. We also calculate an address with the same formula we saw before in episode 8, but now we add 5 bits. The 5 most significant bits are added to the value of address, and this is a direct consequence of the memory map we've chosen. This just means that we are appending 5 ones in the 5 most significant bits of the value of address, so this corresponds to the video memory, which is what we are writing into, to the video memory in this case, the dual-ported video memory. Now, then we set the shift register with address and token. In other words, we are going to do this. We are going to input into the shift register the 16 bits of address and the 8 bits of token, and then the 24 positions of the shift register will be populated. Once that is the case, only then we say that the shift register output enable goes high. In other words, only then do we enable the outputs of the shift register. If we do it before, the output will be enabled while we are shifting things in, and the address will keep on changing, the data will keep on changing, we will add a lot of noise to the system. That's not a good thing to do. So we only enable the outputs once everything has been shifted into the shift register. Then we will set the video read-write signal to low, meaning we want to write into the video memory. And then we will set the video chip enable to low, meaning now we enable the dual-ported video memory. Before that, it's disabled. And then, and that's a different thing from what I did before, then we will get into a loop that will keep on repeating itself, doing nothing, until the video busy signal is inactive. Remember, it's active low. That's why there is this inversion here. So for as long as it's low, we will keep on reading it and doing nothing but reading it. Once it goes high, then this condition here will fail and it will trickle through to the next statement, which is to disable the video memory by setting VCE high, and then we change the read-write state for video by setting it high. You don't want to have the read-write low, because then you're telling the system that you want to write, and things may end up working in such a way that you write noise to the memory just because of electrical fluctuations. This does happen, at least in a prototype, it does happen. So we want to make sure to set the RW of the video memory back to high, to disable it as soon as we are done with the writing. And we disable the outputs of the shift register as well. That's basically it. So if this whole thing works, then we should have the same result we had last time, meaning we will fill the screen with access, then we will clear it, and then we will fill it with access again, and then we will clear it. It should be the same thing we saw in episode 8, except that this time there should be no writing errors, because this time not only are we taking care of this with this while function, we tried to do the same thing in episode 8, it didn't work, but that was because I forgot to put a little, was it a pull-up or a pull-down resistor? And I have the circuit in front of me so I can look at it. It's a small pull-up resistor that I had to add to the VBZ output of the video memory, the dual-ported RAM, and I forgot to do it in episode 8. Now I'm doing it, so now this should work perfectly. So now we should have no writing errors while we are going through the loop. Let's have a look. Okay, so here we have the latest version of CERBERUS video. It's very stable, has a little linear regulator, everything's working perfectly fine here. I'm still using the Arduino MEGA instead of the ATF1508P chip. This is only for prototyping because it's convenient. Shortly I will swap this for the actual chip that will be on CERBERUS. Here on this adapter here we have a 84-pin PLC chip, which is a complex programmable logic device configured with the spacer logic. It's right here. Here we have the connections these are basically the data bus, the address bus, and the control bus, and they go to one side of the video memory, which is a dual-ported memory. The other side is scanned by Cavia in here. There is a little decoupling capacitor here. There are some pull-down and pull-up resistors here at the back. And the reason for those is we cannot leave any bus line undefined. So if spacer is not driving a bus line, then the pull-up and pull-down resistors will define the value. This dual-ported memory always needs to have a defined value for every address line. There is a special pull-up resistor here for the busy signal that's specified in the datasheet. I didn't use this before, and I think that's partly the reason why I was not getting perfect avoidance of the busy signal in the previous episode. Now I am getting it. That there is no mistake in writing or reading anything. This is a little inverter I've built. It's the same thing that this transistor does here in the video part. This is a general purpose transistor with the two 10k ohm resistors, and this basically inverts a signal. If the signal is low, it goes high. If it's high, it becomes low. And they control here through these two wires the output enables of this buffer chip, from which the clock signal goes in and then goes into a spacer here. So this buffer chip is not enabled until spacer is fully on. For now, I'm using a 25.175 MHz oscillator. I will be using a 16 MHz oscillator in the final version. It's just that I don't have one handy right now. I'm using a faster one because if everything works for the faster one, then everything will work for the slower one. This is just a filter capacitor to filter out the CPU clock that comes out of this buffer. I can show you how important this is. If we have a look at the clock signal there, it seems that it's not clean, but if I remove this filter capacitor, look at what happens. You see, you get these spikes, and that's not really nice. So we just filter that out with this capacitor. As you see on the screen, the reads and writes are working perfectly. I'm printing X's on all the positions, all character positions in the video memory, and then I'm clearing the screen by printing spaces. Nothing ever goes amiss, so the logic is working fine. But the logic for taking care of the busy signal regarding spacer, as far as spacer is concerned, is taken care of by the microcontroller in the Arduino sketch. I want to see whether it will work once I put the two CPUs here. The breadboard is big enough to do the entire prototype of CERBERUS here. What spacer does, as we've seen before, it will stop the clock, the CPU clock, when there is a busy signal active under the right circumstances. So to avoid trying to perform a write to the video memory that will not work, spacer will withdraw the clock from the CPUs. It's difficult to test that, but that's what I'm going to try to do now. So with channel A, channel 1 of my oscilloscope in yellow, that's the yellow probe here with the yellow signal for the yellow wire for ground, I'll measure the CPU clock that comes out of spacer. It comes out of spacer, goes through the buffer, and then comes out here on the other side. So it's from here that it would go to this, that it will go to the CPUs. And with the other probe 2, or the blue probe, I want to check the busy signal that is produced by the dual-ported memory. And the idea is to see whether the clock will be withdrawn, as it should, when the busy signal is active. In other words, when it's low. Now, not every time that the busy signal goes low, the clock should be withdrawn. For instance, because of the pull-down resistors in the address bus, even if spacer is not driving the address bus, is not trying to write anything to the video memory, there will still be a busy signal because Kavia will be scanning all the addresses, including address 0. So every now and then there will be a conflict, even if spacer is not trying to write anything. So that's why the logic in spacer is a little bit more complex than to just check the busy signal. It's checking whether the chip enable of the right chip is also active, whether the read-write is a write, in other words, low, and then whether the busy signal is low. So what we need to see here is whether, at least occasionally, when the line in blue goes low, the clock is withdrawn. That will not happen every time that the line in blue goes low, in other words, when it's busy, because as I just said, sometimes the busy signal doesn't require the CPU clock to be withdrawn, but every now and then it should, and that's what I'm going to try to hunt for now, is whether I can see that at least now and then. Now, this will happen very rarely, once many thousands of cycles. So we'll have to configure the oscilloscope properly for that. So channel 2 in blue is the busy signal. So we need to trigger on the busy signal going low So instead of triggering on channel 1, I'll trigger on channel 2, and then the slope going low. That will be the trigger. And you see now we catch every now and then the busy signal going low. Yeah, there we go. So it happened again, but the clock was not withdrawn. So let me think, how will I do this? I think I'll do the following. I will set the trigger in normal mode. Oh yeah, there we go. Ah, we got it. Faster than I thought. I froze it now. You see the busy signal goes low, goes active, and the CPU clock is withdrawn until the busy signal goes inactive. In other words, goes high. That's exactly what I was looking for. That doesn't mean that the clock logic is working perfectly, but if it is working perfectly, we would expect to see something like this. So it's not guaranteed that it's working perfectly in every case, but this is a pretty good indication that everything is going as planned. Let me unfreeze it and see if we can catch it again. So you see here the busy signal goes low, but the clock is not withdrawn. So there are 3 conditions to be met. The other 2 were not met in this case. Let me unfreeze again. Let's see if we can catch it again. Oh yeah, we got it again. See, the busy signal went low, and the clock was briefly withdrawn. So it was a short conflict. The conflict only happens when the X's are being written or the screen is being cleared, not in this interval that you see right now. So now the X's are written, it's clear, now there is an interval. In that interval, nothing happens. So we expect to see this only when something is being written on the screen. Let's do one last try. Yeah, it already happened again. It already happened again. Busy went active and the clock was withdrawn. So we can catch it, even though it happens only once every several thousands of cycles. We can catch it. Let's see. 3rd time. Yeah, it already happened again. You see? Went active, low, and the clock was briefly, very briefly withdrawn here. Sometimes the busy signal goes low for a long time, but it doesn't withdraw the clock because the other conditions are not being met. So here again. So usually it's very brief. The clock withdrawn is very brief. And when it does happen, usually it's brief, which is a good sign. Performance will not be compromised at all by having to avoid this conflict. I'm trying to see it for one last time. Yeah, there we go. There it is again. Busy goes low. Under the right circumstances, the other 2 conditions are met and the clock is withdrawn. So this is looking good. Now the other thing we can measure, we can test, is whether the clock speed logic is working. So here we have the clock coming out. Let me change this to trigger on channel 1, so we have a stable picture. There we go. Channel 2 is in blue here. I'm going to measure the reference clock in channel 2, which should be here, I think. Yeah, that's the reference clock. So now we can test the different conditions by moving these jumpers here between ground and VCC. I think the fastest clock is in this condition when both CPU choice and clock speed choice are high. And then what we get, the CPU clock should be half the reference clock, so the maximum CPU clock should be 8 megahertz compared to the 16 megahertz at which the microcontroller will be running. This is the reference here is 25 because I don't have the right crystal right now, but it doesn't matter. So so long as the yellow is half the blue, it should be right, and that's exactly what's right. So one blue clock cycle goes from here to here, and the yellow one goes from here to here. So it has two of the blue in one yellow clock cycle, which is exactly as it should be. Now if I now change the CPU choice, let me see, this is the second possibility. Let me have a look what this means. So in this one here, if this is 16 megahertz, then this should be 2 megahertz. So that's divided by 8. And so we should have 8 of the blue cycles in one yellow cycle. So one yellow cycle goes from here to here. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8. That's exactly right. And now if we choose the Z80 at the slow clock speed, then we get this condition here, in which the CPU clock should be 1 megahertz when the reference clock, or the 16 megahertz for the ATmega controller, is 16. So we divide by 16. So between this point and this point, we should have 16 of the blue clock cycles. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's just right. That's working perfectly as well. So this has been an extra long XL Christmas special of the Cerberus saga. I hope you've enjoyed it. It's been very densely packed with information. I hope you've been able to follow. It's hard to avoid a lot of this when you're trying to share computer design with other people. There are things you have to try to explain and share. I hope it's been enjoyable nonetheless. I wish you great holidays. I don't think the next episode will come out before the turn of the year, so I also wish you a Happy New Year, and I will see you next year with more of Cerberus. I think the difficult part, the big hump on the road is behind us, but there is still a lot of labor ahead, which is also worthwhile to follow. Okay, Happy New Year, and I will see you then. If you've been paying very close attention to these episodes, you will have noticed that this diagram, this schematic that I showed you in episode 9, particularly this part here, the lower part, if you've been paying attention, you have noticed that this is not consistent with the spacer hardware description that I showed you today. If you've noticed this, kudos to you, you are with me, you are on. The correct version of this that is consistent with the hardware description would be this one. It would have the shift register state 23 as the rightmost one, and the most significant bit of data being the one corresponding to the rightmost flip-flop, and that goes down to D0, and then we start with the address bit 15 and all the way down to address bit 0, and the leftmost state in the shift register would be shift register 0, corresponding to A0. That's what is actually in the hardware description.